Here's a different kind of problem which will test our ability to write down Newton's law and figure out the frequency of vibration. Here we have a small massive ball. It's held between these two rubber bands. I know intuitively if I displace the ball slightly and let it go, it's going to vibrate back and forth. Our job is going to be, number one, write down the force on the ball, and then, number two, from that force, figure out what the frequency of vibration is going to be. This thing is not a mass on a spring. It's not a pendulum, so I can't just go back to our general equations for the values of omega. We have to kind of start from scratch. Okay, so first of all, the displacement is assumed to be very small so that the rubber bands barely stretch when you displace, and therefore the tension just stays constant. We're told to assume that. So let's sketch what we have here. Here's the ball when it's been displaced slightly. And let's look at the forces that act on the ball. The rubber bands pull at an angle on both sides of the ball like this. Equal tension on both sides, just different directions. T and T. Now we're told that the angle, we're told the displacement is Y. What I need to think about is the angle for a second, because I need to think about the components of the forces in the Y direction. I'm going to write down the net force in the Y direction on the ball, and from that figure out the frequency. Notice that if this is angle theta, then it's the same angle with the horizontal here. So this is theta, and this is theta as well. Therefore, the net force in the Y direction, it's equal to 2, because there are two tensions, 2t sine of theta. Sine theta will give me the component of the tension which points downwards in the Y direction. And notice it is downwards, so I need a minus sign. Okay, now if Y is very small, then I can use my small angle approximation, and this is just going to be minus 2t times theta. Now notice this is the same thing, since the angle is small, theta is equal to theta divided by 1. That's just an obvious thing. Theta is equal to theta divided by 1, and that's sine theta divided by cos theta for small angles. Remember, sine of theta is nearly theta. Cos theta is very nearly 1. That means that for very small angles, sine theta is nearly theta, which is just basically sine divided by cosine, in other words, tangent. So this is approximately just minus 2t tan theta. Why tan theta? Well, tan theta is easy. Tan theta is y divided by L, opposite over adjacent. So this is just minus 2t divided by L times y. Why did we go through the trouble of simplifying sine of theta for small angles? Because now you see the net force on the ball is just proportional to the displacement. Sound familiar? Sure, just like a spring or a pendulum. The force that acts on it is just proportional to the displacement, so I know it's going to be a simple harmonic oscillator. So what's the frequency going to be? By the way, we've answered question A, find the restoring force. To find the frequency of the motion, I should write down the acceleration of the ball. This is the net force from the rubber bands. If I release the ball, then it will be set into motion, and I can now predict what its acceleration is at any moment that it's at position y. The acceleration in the y direction is the net force in the y direction divided by the mass of the ball, and that gives me minus 2t over ml multiplied by y. So is this thing a simple harmonic oscillator? Sure it is. I better go compare it to the general rule for simple harmonic motion, which is that the acceleration in the y direction would be minus omega squared times y. And so that sure is a simple harmonic oscillator. This constant here is omega squared. And so we've answered the question we were asked, which is, what's the value of omega? It's the square root of 2t over ml. So there we go. That's how we start from scratch, writing the forces, and from that figure out what the frequency of motion must be. Next, we encounter something like a mass on a spring, except it's a wheel on a spring. This means we have to use the torque method, write down Newton's law in the torque form of it, so we can do the usual thing, which is figure out the angular frequency of the small oscillations of the system. Okay, so let's think about how this works. We imagine displacing the wheel slightly, turning it a little bit, small angle of displacement. When I let it go, I know intuitively it's going to vibrate back and forth. Our job is to figure out the frequency of that vibration. Okay, let's draw a sketch. Here's the wheel in its vertical position. By vertical, I mean when the attachment point is vertical here. Now, when I turn the wheel, this attachment point at little r turns a little bit, and now it goes down here. What I need to do is write the torque that the spring gives to the wheel when it's been displaced to an angle theta. Here's theta. Notice that I'm exaggerating the angle because we're supposed to assume a very small angle of displacement, okay? If the angle's very small, then the spring stays basically horizontal as the wheel turns out. So the spring is now, I'm assuming, still horizontal. Again, that's only true for a very small angle. My picture exaggerates it. But I'm going to assume that the spring is horizontal. Here's x now. X is the stretch of the spring. You see now that the wheel's turned, the spring is stretched out a distance x. Okay, this is all little r, the radius at which the spring is attached at. Okay, I need to write down the torque that the spring gives. Let's do that. The torque from the spring. It is, let me say, it's approximately just r kx with a minus sign. Minus sign because when it's displaced to the right, the torque is back to the left or counterclockwise and vice versa. Now, you might complain that the force of the spring is not perpendicular to this radius r. And so I need some kind of a angle factor in here to get it right. And you're correct. However, for super small angles, little r and x remain, essentially perpendicular to each other. And so although my picture looks like r and x are certainly not perpendicular, for very small angles, they nearly are. And so this is an accurate equation for the torque. Okay, now I need to write down x in terms of the angle theta. So let's do that. This is minus r times k times x. And how big is x? Well, it's r sine of theta. And that's exact for my figure. But again, we're assuming small angles, and so this simplifies to be minus r squared, or let's say minus kr squared theta. So it was crucial that I assumed small angle. That simplified the torque down greatly so I can actually solve the problem. Okay, so that's the torque. What do I do with torque? I set it equal to the rotational inertia times the angular acceleration. It's equal to the net torque minus k r squared theta. In other words, the angular acceleration is equal to, I should remind us what the inertia of a wheel is. Since all the mass of the wheel is at the same radius, capital R, from the center, the inertia of it is just mr squared. So when I plug that in for the inertia and solve for alpha, I get minus k. It's r squared, little r squared, over m, big R squared, times theta. Is this a simple harmonic oscillator? We should be able to immediately tell it is, because the acceleration's proportional to the displacement. Remember again the general rule for simple harmonic motion, that the acceleration must be equal to minus omega squared times the displacement. This is linear displacement and linear acceleration, but the same thing works for angular displacement and angular acceleration. So therefore, by comparing these two, I can read off the frequency of the motion. Omega is r over r. I take the square root of this. I get r over r times root k over m. Kind of like a mass on a spring, which is root k over m, but the radius at which the spring is attached at makes a difference. Notice that if r equals the radius of the wheel, this factor cancels, and then it is just root k over m. If you attach it right at the edge, it does act exactly like just a mass on a spring. What if little r is equal to 0? Then nothing happens. If little r is 0, there is 0 frequency. Makes a lot of sense. You can't make a wheel vibrate by attaching it at the axle. Here's a pendulum with mass that drains out of the bob of the pendulum. Now, one thing to note is it's not drawn to scale. We're supposed to assume that Li, which is the distance from the top to the center of the cube, is way bigger than the size of the cube. So therefore, I'm going to assume it's a simple pendulum. Therefore, I know that I know what its frequency is. Simple pendulum, I know that omega is a square root of g over L, where L is the length from the attachment point to the center of mass of the bob. Now, this has nothing to do with the mass. So on the face of it, we might think, so what if the mass drains out? That has no effect on a pendulum at all. However, there is a slight effect that we need to account for, which is that the distance to the center of mass changes. You see, as the liquid drains out, the center of the liquid is closer to the ground. L increases as time goes on. So our job is just to figure out how L changes, essentially. First, let's write down how the mass changes. We're told that the mass drains out at a constant rate. Okay, that means that the mass of liquid that's in there is going to be the initial mass, the amount of mass at the beginning, call it m naught, minus the rate times time. Now, I'm going to write the initial mass in terms of the density. They tell me the density of the liquid, and I know this is a cube of volume a cubed. So the initial mass would be the density of the liquid times a cubed minus the rate times time. Just telling me how the mass decreases. Okay, what I need really is how the length of the pendulum changes. The length. To figure out the length, what I'll do is I need to locate where the center of mass of the liquid is at any moment. All right, so the length is going to be the length all the way to the bottom of the cube plus, minus h over 2. H is the thickness of the liquid at that moment, and I have to go halfway up to get to the center. So again, to figure out how long the pendulum is, I have to take the total distance all the way to the bottom of the cube and subtract h over 2. So that's just Li plus a over 2. That's the distance all the way to the bottom. And then subtract off h over 2. And that gives me the length at any moment. So that leaves me with figuring out how h changes with time. How does h change with time? It's easy to find it because I can just figure out how the volume of the liquid changes with time. So I need h. H is a function of time. H is the volume of liquid in there divided by a squared. And I'll write that in terms of the density and the mass. The volume of the liquid is the mass of the liquid divided by its density. Okay, so now I know how the mass changes with time, and now I'm set. Now I'll know how the height changes with time. So I plug in m. Notice the initial mass part partially cancels out and leaves me with a minus dm dt. It's the rate. Oops. Divided by rho a squared times time. This is just telling me that the height of the liquid starts at A and it decreases from there. Now I just have, precisely the expression for how it changes. Now I know how the height changes, and I can plug that back into the L value that I need. So L is the initial length to the center plus A over 2 minus H over 2, and that simplifies things down, and I get the initial length plus the mass rate that it drains out divided by rho a squared times time. So the length does increase with time, and therefore the frequency will drop as the liquid drains out. Longer pendulums swing slower. And so, it's not that the frequency depends on the mass, it really just depends on how the length increases as time goes on.